Okay, we're going to focus today on, I guess this is the same day as my previous video I made, but it's still today. So we're going to focus on induction inequality proofs. And induction inequality proofs are substantially different than equality proofs. Equality proofs, if you just do the algebra, generally you can make it work. You can prove the induction step, which is the hard part. You can find the expressions you need. Inequality induction proofs often require some creativity and, as we've already talked about, knowing well the common inequality theorems. So these theorems. You should have your sheet by you, or at least have it open in another screen. These theorems we will use. I want you to refer to them by number in your proofs. And just say inequality. If I use inequality theorem 2, you say inequality theorem 2. But it's just helpful. I want you'll use them enough, as you'll see in inequality induction proofs, that you'll get to know them well. So what we're going to do first of all is focus on a question like this. Find a natural number n such that 3/2 raised to the n, and there we go, I've got my pen handy, 3/2 raised to the n is greater than or equal to n plus 1. That's for all n greater than or equal to n naught. Okay? And so what we're looking for is this number, this natural number n naught, such that anything larger than that makes this expression true. The first step in these inequality proofs is often, now just because of the way we've stated the inequality theorems, is all of the theorems we used in inequalities were stated in terms of less than or equal to. But notice that this expression is greater than or equal to. So let's turn it into a less than or equal to expression just by reversing it. If 3/2 to the n is greater than or equal to n plus 1, then n plus 1 is less than or equal to 3/2 to the n. So we've converted it into a less than expression. Now we're still looking for the natural number n, and to do that, I think the best approach you can do is there's a couple different approaches. You can just start plugging in numbers, and you can get a sense. Plug in the number 1. Okay, so number 1, for example, is, let me go back to my pen. For the number 1, you'd have 1 plus 1, which is 2. Is that less than or equal to 3/2 to the first, which is 3/2? So it's not true for 1. And then you can just keep working up on your numbers. The problem with that is that often students want to stop when they find the first one that works, whereas what is often the case is maybe it works for 1 or 2 sort of sporadically, but at some point, at some n naught, it's going to always be true. And the key is to find that n naught. So tables work if you can do some table on Excel, for example, or on a calculator. What I like to do, I'm going to show you here real quick, is do it on a graphics package. So I have got Desmos here, and what we have is we can just graph each of these expressions. We can say, first of all, the first one is y equals, it was n plus 1, so I'm going to say x plus 1. Okay, so there's y equals x plus 1. My next expression, which will be in blue, is going to be y equals 3/2. 3 divided by 2, and then to make it an exponent, caret to the n, or to the x rather. All right, so what you see is when x is 0, these are equal. Now, and at least from what we see in this window, when x is, what does that turn out to be? I can zoom in a little bit. It looks like a little bit less than 4. When x is a little bit less than 4, they're also equal. Now you might also say, well, okay, maybe somewhere down the road they can switch back. We could actually prove it with calculus. You know, the slope of x plus 1 is constant. It's never going to change. Whereas the slope of 3/2 to the x is always going to be increasing. So these are never going to sort of intersect again. You can prove that with calculus. Or if you like, you can just actually graph the difference between these. So I'm going to graph the difference, y equals, oh, there you go. There we go. So y finally equals the first one, x plus 1, minus the second one, 3 halves raised to the 3 halves raised to the x. And you can see here as I bring this up, you can see it looks like, again, their equality, when they're equals, when it's 0, right above before. So it looks like after 4, let's go back to the expressions, are 3 halves to the x after 4. Okay, so from 4 onward, all right? So 4 would be right, let me get my pen out. Oh, sorry. Our 4 is going to be right in here, right? So from 4 onward, it looks like this is going to be true. So let's go back to the induction. That's how you develop a conjecture. I have a conjecture now. Okay, so my conjecture is that for all n greater or equal to 4, this expression is true. All right. So now that's our expression. So now we want to use induction. Why do I want to use induction? Because I'm trying to prove that this is true for all natural numbers that are greater than 4. It doesn't mean you have to use induction. There might be other ways, but that's a good clue when you can use induction. So let's prove this using induction, which we can do for all n greater or equal to 4. Since the first, so this, again, the important point to note, again, from our class is we're not starting at 1, we're starting at 4. Anything after 4 is when this is true. And again, that is called the extended principle of math induction, when you start at some other value than 1. So our base case is S of 4. So to show S of 4 is true, what we want to do is we want to substitute 4 into both sides. Again, that's one of my little pet peeves. Make sure you do not assume that this expression is true. Now, don't just plug n equals 4 into there, because then you've sort of implicitly suggested that this is a true inequality. Substitute it into both sides, then you're going to use the transitive property of inequalities. If n equals 4, then n plus 1 is 4 plus 1 equals 5. Also, if n equals 1, then plug it into the other side. 3 halves to the n is 3 halves to the 4. It's 5.0625. So what we know is that we know that n plus 1 is less than or equal to 3 halves to the n for n equals 4. That implies that S of 4, our base case, is true. Now comes the fun part, the inductive step. So for the inductive step, we want to show that if S of k basically is true, then S of k plus 1. So this is conditional. So let's assume that S of k is true. In other words, assume that k plus 1 is less than or equal to 3 plus k, 3 halves to the k rather, for some k greater than or equal to 4. It's always good to note, where do you want to go? What's your goal? You want to show that S of k plus 1 is true, which means what you would like to show is you'd like to show that, there you go, you would like to show that k plus 1 is less than or equal to 3 halves to the k plus 1. Okay, so let's work through this. We've assumed that S of k is true, so we can work with that. By Inequality Theorem 3, remember, I kind of want to say, well, this is my thinking. I have 3 halves to the k. I'd like to get 3 halves to the k plus 1. So let's multiply both sides of this inequality by 3 halves. We can do so. That's Inequality Theorem 3, the multiplicative property of inequalities. We can multiply both sides. The inequality still holds. So doing a little bit of algebra, we multiply by 3 halves, distribute the 3 halves, 3 halves k plus 3 halves. It's less than or equal to 3 halves to the k plus 1. What's important to note there, I'm going to draw an arrow to this so you see it, all right, is that side is exactly what we want it to be. Now, we're going to work on our right-hand side. I'm going to break up 3 halves k to k plus 1 half k. The reason I did that, because I'm trying to match up the sides. My right-hand side works, is okay. I need to get a k in my left-hand side, so I can take it out of the 3 halves k, and I'm left with 1 half k plus 3 halves. Now what we're going to do is, well, how do you get the other values? 1/2 is or 3/2 is not our 1. Now we're going to use what we know about our k. We know that k is greater or equal to 4, so I'm going to substitute that k is greater or equal to 4. So if k is greater or equal to 4, then I know that 4 is less than or equal to k. I just turned it into a less than. So what I'm looking at is I'm looking at this piece right here. So essentially I'm going to substitute 4 in. So 1/2 to 4, times 4 rather, is less than or equal to 1/2 k, and that's by theorem 3. Essentially we can multiply both sides of this inequality by 1/2. So that means that 2 is less than or equal to 1/2 k. Now what I'm going to do is I'm going to substitute. I know that k plus 1/2 k plus 3/2 is less than or equal to 3/2 to the k plus 1. So I'm going to substitute something smaller in for that 1/2 k, which is our 2. And that's how you get your 2 in there. So I have a little bit of algebra when I do that substitution. This is inequality 7. K plus 2 plus 3/2 is less than or equal to 3/2 to the k plus 1. Pretty close to being done. All right, so now I'm going to break it up. I'm going to say, well, I know that 2 is, I'd use a little algebra again, I guess, we know that 2 is 1 plus 1. And you might say, well, why did he do that? Because remember, on our what we're trying to get to, remember the goal, we're trying to get to 1 plus 1. Well, this right here is my 2. So I know that k plus 1 plus 1, but we also have our 3/2 is less than or equal to 3/2 to the k plus 1. And now this is where those inequality theorems are so useful. What we have is that k plus 1 plus 1 plus 3/2 are all less than or equal to 3/2 to the k plus 1. Notice that each of these pieces is greater than or equal to 0. That's greater than or equal to 0, or not negative. This is greater than or equal to 0, also not negative. And that's where inequality 2 is so important. Basically it says if a plus b is less than or equal to c, then I know that a is less than or equal to b, or c rather, and b is less than or equal to c. In other words, since they're all positive, each piece has to be less than or equal to the c. So what I have is I call this piece down here my a. Since a plus b, which is the 3/2, is less than or equal to 3/2 to the k plus 1, each piece. So that says that my a alone, which is this, is less than or equal to 3/2 to the k plus 1. And that is my s of k plus 1. So you have to use inequality 2 in order to make that last step. So to finish off, I want to just state a conclusion. I know that, just look back at what I've done. I've said if my s of k is true, I know that my s of k plus 1 is true. So now to sum it up, we know that since s of k is true, s of 4 is true rather, and s of k implies s of k plus 1 is true, which is the inductive step right here, and that's for k is greater than or equal to 4, then that implies that n plus 1 is less than or equal to 3/2 to the n for all n greater than or equal to 4.